So here we have another dynamics problem that requires working in the polar coordinate system. Specifically, we have a satellite that's tracking a rocket, and we want to find out what the velocity and acceleration of the rocket is, given certain values of how the satellite is rotating. So I've already gone out here and written down all the values that were given, and I've already converted the r radius to meters from kilometers. And now, first step is going to be to rewrite this diagram on a series of standard axes so we can work with it without all the pictures, assuming that the rocket's a point and the satellite's also a point. So here's our coordinate system. It's going to be the standard x and y. And here at the origin is going to be where our satellite is, and a certain distance away, an r distance away, is going to be where the rocket is. So let's say here. And drawing the radius arm, and this is our angle theta, and this is the path that the rocket is traveling on. So similar to the road problem. However, at that point we were given the velocity and we're basically told to solve for these values in polar coordinate system. Now we're given the values and we're trying to find the velocity and acceleration. Well, if, once again, this is our standard xy, this is our r and our theta. So if this is the r direction axis, the r axis direction, that means that this must be the angle, or where our positive theta axis is, and this is our negative theta axis. And we know that the velocity, as given here, the velocity of this rocket is moving upwards, and so is the acceleration. So we're going to be solving for velocity first, but here is the velocity of the rocket, which we don't know. But we do know that, once again, if we draw perpendicular lines, we know that this is the component of this velocity in the r direction. This is the component of this velocity in the theta direction. And we know from the formulas that they're given to us, but you could also derive them. They're very long and they require several derivatives. But we know that we have our v theta is equal to r theta dot. And that's one of the given values. Well, we are given theta dot, we are given r, and we can solve for v theta. So we have v theta is equal to r being 9,000 meters, theta dot being 0.02 radians, and this ends up being 180 meters per second. Well, what's the relationship between v theta and v? Because we can use that to find our velocity. Well, if we draw in a mini x-axis here, just a translated version of the location of the x-axis. Well, if this is theta, then this must also be theta. And if the r-axis is just a rotation upwards of theta from where our standard x-axis would be, let's say x prime, well, the theta axis is just that same angle rotation from where our y prime axis is. So this is also theta. Well, now we have a relationship between v theta and v. We can say that cosine of theta is equal to v theta over v. And we can rewrite this as v is equal to v theta over cosine theta. Well, we know the values for v theta and cosine theta, so we can rewrite this as v is equal to 180 over cosine of 60. And that ends up giving us that our velocity is equal to 360 meters per second. And that's our first answer. So that is the linear velocity, in this case, in the positive y direction. And we figured that out using the polar coordinate system given values in the polar coordinate system. So now we're going to move on to solving for the acceleration. Well, we also know that the acceleration in the r direction is given to us as r double dot minus r theta dot squared. And the values that we know here, we know that r double dot is 21 meters per second squared. We know that r is 9,000 meters. And we know that theta dot is 0.20 radians per second. So we know that our acceleration in the r direction is equal to 21 minus 9,000 times, and then this is 0.02 squared. And this ends up giving us that our AR is equal to 17.4 meters per second squared. Now we're not done yet. We know AR, but we want to figure out what our acceleration is. Because if we redraw this whole diagram, hold on. If we redraw this whole diagram, I'm just going to copy and paste it. We would have a very similar diagram, except this time we would be solving for acceleration. So if we just rewrite this as a of r, a of theta, and this, besides being velocity, is our acceleration because it's in the same direction, so it'll be our acceleration. Well, how do we solve this? Very similarly. Now that we have AR, a relationship between AR and our A would be that AR, or we would know that this angle here is just 90 minus theta, or in this case 30 degrees. So we know that cosine of 30 degrees is equal to AR over A. And this can be rewritten as A is equal to AR over cosine of 30 degrees. Well, we know AR, and we know what cosine of 30 degrees is. So we can solve this as A is equal to 17.4 over cosine of 30, which is equal to 20.1 meters per second squared. And that's equal to our A. So this is a lot simpler, a lot faster, but it shows how switching and relating values in the polar coordinate system to a standard rectangular system, you could solve very interesting things.